Hello friends, in this video we are going to study about the time response analysis of a second order control system when the input is a unit ramp function. So let's start with our topic. We know that a second order control system, its transfer function, it is given by it is the generalized or the standard form of transfer function for a second order control system. Now, this is the transfer function. So if we cross multiply this, that is Rs is multiplied to this right hand side, shifted to this. So we have Cs equals to Rs multiplied with omega n square upon s square plus 2 del omega ns plus omega n squared. So we have to find out the time response analysis of a second order control system, and input is unit ramp function. So this Rs is the input. We apply the input Rt, and Rs is the Laplace transform of this input function. Okay. So Rt we have given that it is a unit ramp function. So Rt will be equals to T. And if we take the Laplace transform, that is Rs, so it will be equal to 1 upon s square. So if we put the value of this Rs here, that is 1 upon s square, and we can get this Cs, that is the Laplace transform of the output. And if we take the inverse Laplace transform of this Cs, we will get Ct, that is the output, or we can say the time response of the system. So we have to put the value of Rs here, then solve it, take the inverse Laplace transform and get the value of Ct. So Cs, here we will put the value of Rs, that is 1 upon s square, and the transfer function is omega n square upon s square plus 2 del omega ns plus omega n square. Now this is, we have to get the partial fractions, or we have to convert this term into the standard formulas so that we can apply those formulas directly to get the inverse Laplace transform. So first we will get the partial fractions of this term. Okay, so partial fractions will be a by s plus b by s square plus cs plus d upon this is how we can get the partial fractions of this term. So what we are going to do, we will get the value of a, b, c and d so that we can have this partial fractions term. Okay, so for this we have a by s plus b by s square plus and this will be equated to this term. Get the LCM here. So LCM will be a, here we have s, so we will multiply a with s square plus 2 del omega ns plus omega n square plus b multiplied with s square plus 2 del omega ns plus omega n square plus Cs plus D multiplied with S square. So what we have done, we have get the LCM and then we have multiplied all these and this will be equated to this term. So the LCM is same. So we are going to equate this numerator parts of both these halves because both sides of equations we are going to equate the numerator parts. Okay. So here we will simplify this and we will get the coefficients of s cube, s square, s and the constant terms. So the coefficient of s cube, s square and s on both the sides, if we see on the right hand side we have no coefficients, they are 0. There is no term of s cube, s square, s and okay. So the coefficients will be equated to 0 and constant terms they will be equated to omega n square. So when we will solve this, we will get the value of A, B, C and D. The 4 parameters we are going to get. So the value will come out to be, I am directly writing the value. You can solve this and can get these values A, B, C and D. So A will come out to be minus 2 del upon omega n. B will come out to be 1. C is 2 del upon omega n. And D is minus 1 plus 4 del square. So we are going to put the values of these A, B, C, D parameters in this and we will find out the partial fractions of this term CS. So CS will be A is minus 2 del upon omega n, then S plus B is 1, so 1 upon S square plus C into S, so 2 del upon omega n S plus D, that is 4 del square minus 1 upon we have S square plus 2 del omega ns plus omega n square. So what we have done, we have put the values of A, B, C and D in this equation. A was minus 2 del upon omega n. So we have written minus 2 del upon omega n and multiplied with S here. Then B was 1. So we have written 1 upon S square here. Then C was 2 del upon omega n. So we have written here 2 del upon omega n multiplied with S here. And then the value of D, that is 4 del square minus 1. And the denominator equation we have written here. So we have got CS. Now we will simplify this. So here we are going to add here S plus del omega n and minus omega n. This S will be replaced by, we will add plus del omega n and we will subtract del omega n. So CS will be and this plus 4 del square minus 1 is as it is. So we have added del omega n and we have also subtracted del omega n. So the equation is not changed. This term S is not changed here. Okay. So now CS equals to so we have got this term when we have added and subtracted del omega n. So we can put S plus del omega n. We can multiply it with 2 del by omega n and then minus 2 del omega n multiplied with this del omega n. So this S plus del omega n, it is taken as one term and this is taken as the second term. And we are multiplying this with this and then this second term with this. So what we have written, 2 del omega n multiplied with S plus del omega n minus 2 del omega n multiplied with del omega n. and rest of the terms are as it is. Now in the denominator we were having s square plus 2 del omega ns plus omega n square. So here we can take here common s plus del omega n square. We have reduced it into the form s plus del omega n square plus omega n square 1 minus del square. Here also we have added and subtracted del omega n. Okay, so del omega n, if we will write here, it will form the formula s plus del omega n whole square, and omega n square, if we write here, we can add del square omega n square, and we can subtract del square omega n square. Okay, so this s square plus 2 del omega ns and plus del square omega n square, it is forming the formula s plus del omega n whole square, and remaining terms we can take omega n square as common, so we are left with 1 minus del square. So we have written it here. So we are just simplifying this so that we can reduce it to some of the standard formulas of inverse Laplace transforms. Now this omega n and omega n, they can be cancelled out. Okay, and just simplify it more. Now this omega n and omega n, they are cancelled out, so we are left with 2 del square. Okay, minus 2 del square. Now multiply this, we have this term. Okay, this term we have written here 2 del upon omega n, s plus del omega n, and the denominator as it is. Then plus sign, because we have here minus 2 del square, and here we have 4 del square minus 1. So 2 del square and 4 del square, we are left with 2 del square and then minus 1, and the denominator term is as it is. Okay, now we know that omega d is equal to omega n under root of 1 minus del square. So omega d square will be omega n square 1 minus del square. So omega n square 1 minus del square, we can write it as omega d square. Okay, so we are writing here omega d. Okay, so here in place of omega n square 1 minus del square, we will write omega d square. So cs equal to 1 upon s square minus 2 del upon omega ns So we have replaced this by omega d square. So we can write 1 upon s square minus 2 del upon omega ns. We have written it here. Then plus 2 del upon omega n. This is, we have written as it is. Then s plus del omega n square, and plus this omega n square, we have replaced it by omega d square. Now here we have 2 del square minus 1. So we have written 2 del square minus 1. Then we have multiplied and divide this term by omega d, so as to convert it into the sum of the standard form. So this is multiplying and dividing with omega d, so there will be no effect, and the rest denominator term we have written as it. Now we will take the inverse Laplace transform of this CS. So we will get CT. This is 1 upon s square. So its inverse Laplace transform will be t. Then minus This is 2 del omega n, it is a constant, and this is 1 by s. So 1 by s, its inverse Laplace transform will be 1 because it is a unit step function. So it is minus 2 del upon omega n plus 2 del omega n, it is again constant. So written as it is. Then this will form the inverse Laplace transform of e raised to the power minus del omega n t and cos of omega d t. Because this is e raised to the power minus at cos of at here, cos omega t here. So this is s plus a upon s plus a square plus omega square. This is forming the inverse Laplace transform standard formula. So we have just replace it by e raised to the power minus del omega n t and cos of omega d t. And this 2 del square minus 1 upon omega d, it is a constant, so we can write it as it is. And this is forming the inverse Laplace transform of e raised to the power minus del omega n t sine of omega d t. Okay, so we can apply the standard inverse Laplace transform formulas. This is for e raised to the power minus at cos omega t, and this is for e raised to the power minus at sine omega t. Now let's simplify this. Now in this we have t as it is minus 2 del upon omega n as it is plus 2 del. Now omega n, it can be written as, here we have omega n, so we can multiply and divide it by under root of 1 minus del square. And rest of the term is as it is. Here we have 2 del square minus 1, and omega d can be written as omega n under root of 1 minus del square. And rest of the terms are as it is. Now we are going to multiply this inside. Okay, so we have ct t minus 2 del upon, this is 2 del under root of 1 minus del square multiplied with this. We can take common from these two terms, this e raised to the power minus del omega nt and the denominator term. So taking common, we are left with here inside we are left with 2 del square minus 1. Now let us suppose that 2 del under root of 1 minus del square, it is equal to sine phi, and 2 del square minus 1, it is equal to cos phi. We are doing this because we want to convert it into the formula sine A cos B plus cos A sine B. Okay, so we are converting it into the form sine phi. We are assuming this as sine phi, and we are assuming this as cos phi. So it will be converting into sine phi cos omega dt plus cos phi sine omega dt. That is sine A cos B plus cos A sine B. Okay, so just put the values here. We have ct equals to t minus 2 del upon omega n. Now we will apply the formula here. This is the formula for sin A plus B. Okay, that is sin A cos B plus cos A sin B. It is equal to sin A plus B. Now, here phi is equal to tan inverse of 2 del. How we have obtained this? If we want tan phi, then it is equal to sin phi upon cos phi. Okay, sin phi we have supposed this value and cos phi is this. So tan phi will be sin phi, that is 2 del under root of 1 minus del square upon 2 del square minus 1. So phi will be equals to tan inverse of this term, and we have written it here. Phi is equal to tan inverse of 2 del under root of 1 minus del square upon 2 del square minus 1. So we can directly calculate this phi value and put it here, and we can obtain the output response. So this is the output response of a second order control system when the input is a unit ramp function. Now, if we want to calculate the error signal, so error signal is given by this was our CT, and the input was unit ramp function. So error signal, it is the ET, which is the difference of input and the output. Now input is a unit ramp function, so RT will be equals to T. So ET will be equals to RT is T, and then put the value of this CT here. So it will be minus T minus plus 2 del upon omega n minus e raised to. So this T and T, they will be cancelled out. Okay, and we will get the error signal as 2 del upon omega n minus this is our error signal. Now if we want to find out the steady state error, so steady state error is given by ESS equals to limits S tends this T tends to infinity ET. So in this equation, if we put the limits T tends to infinity, so what we will get? This constant term. If T is infinity, so it will become 0. So we are left with only 2 del upon omega n. So this is the steady state error for a second order control system when the input is a unit ramp function. Now if we want to draw the response of this, okay, then its response will be like this is our input, that is T, and our output will be so we have the input is our straight line, this, and output is like this. So the deviation of the output from the input, it is the error which is called the steady state error, and its value is 2 del upon omega n, and it is the time by which the output is lagging behind the input. So this is also called the lagging time, 2 del upon omega n. So this is the time response of a second order control system, for a second order control system when the input is a unit ramp function. So I hope that this video is clear to you, that how the time response for a second order control system can be calculated when the input is a unit ramp function. So thank you.